Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for those who are in pre-calculus and just need a brief kind of build up on their graphing skills prior to entering calculus. There are a lot of little things that you kind of have to pull together with graphing when you step into a calculus course. It is assumed that you know how to use the transformations of functions. If you don't, I have a series of videos on non-rigid transformations of functions and rigid transformations of functions for you to review. It is not necessary to review those if you have already had intermediate algebra and college algebra. At this point, you should already know how to actually manipulate functions given vertical or horizontal shifts, or vertical or horizontal stretches or compressions, or reflections about the axes. This video is really dedicated to build onto that one extra little piece, which is looking at the absolute value of pieces of those functions and graphing non-standard functions. The standard functions are things like the square root of x, or x squared, or the absolute value of x, natural log of x, e to the x, sine of x, all that stuff. Those are the standard functions you know the base functions or the base graphs for, but we're actually going to build on that a little bit here. It won't look like it at first. Let's go ahead and sketch the graph of this function g of x. We're not going to plot points, we're going to use transformations. But at the end of it is really the new material. We're going to go ahead and graph the absolute value of g of x. It's a minor, very, very minor change up in the end. So I'm using really this first example here to remind you of all your transformations. Let's start by getting this in a good form. A good form is a form as follows. In this case, if you can get a function in this format, you're pretty good, because A would simultaneously represent any type of vertical reflection about the x-axis and a vertical stretch or compression by a factor of A. And I'm trying to fit all the information here, but I had to zoom out a little bit to make more room. Notice here I say if the absolute value of A is greater than 1. Because if A is negative, we have a reflection about the x-axis. But if in magnitude, the absolute value of A is greater than 1, we're also stretching that function away from the x-axis in the vertical direction. Essentially, you're multiplying all the y values by A. If, on the other hand, the magnitude of A is between 0 and 1, then all the y values are being multiplied by a number that is in magnitude less than 1, so everything gets compressed, and it gets compressed vertically by a factor of A. So if A was like a half, everything is half its original size. So let's go ahead and start with g of x here, trying to figure out really what the base function is, what A is. The trick with rational functions, which are kind of the odd ones on the block when it comes to the base functions, is that you want the numerator here to be a 1. And the coefficient of x, well, I would say the coefficient of the x squared term to be 1. And it's not really the coefficient of x squared either, but whatever. We want that number here to be a 1 as well. So what we're going to do is factor a 3/7 off of this fraction. So we'll have a negative 3 over 7, and we're left with 1 over. Now, I'm also going to do a little manipulation here, because notice in my notation, if I have an argument of f that is a linear function, but it also has a coefficient on x that's not 1, I'm going to factor that off of both the coefficient of x and that last constant. Here's what I mean. We go over here and we have something squared. That's the first step. You have something squared downstairs. We already factored off the 7 off that denominator, so I don't care about that. But what we're going to do is factor an 8 off of both this 4 and this 8x. So I'll bring an 8 off of both of them, and I'll be left with x minus 1/2. You could double check my work by distributing that 8 back through, but I'm going to guarantee that it's correct. Finally, I'll write the +1 on the back end. This gives me all the information I need to appropriately graph this function. First of all, the fact that the coefficient a is a negative number, I know this is reflected about the x-axis. Also, notice that this coefficient right here in magnitude will be of size 3/7. That is less than 1, and therefore this is going to look just like the base graph, which we'll talk about in a moment, but it gets compressed by a factor of 3/7. So I'll just cross out this piece right here because we're not using it in this problem. Now let's zoom in to what b does. Now that we have a taken care of, we now need to know what happens with b. Well, if a multiplying our function caused a stretch or a compression vertically, then from our prereq knowledge, the b as a coefficient of x causes a stretch or a compression horizontally. However, because it's inside the function, it's actually the opposite of what we would normally think. The only thing that's not opposite of what you would think is this part right here. If b, which is the coefficient of x in the argument of our function here, if b is negative, then it's going to be a reflection about the y-axis of the original function. And in this case, I might as well just say it, the original function, if you strip away all of these numbers, I'll just do that. If you strip away all these numbers, even this guy right here, even the negative right here, you pretty much just have an x being squared. And that's really the base graph, 1/x squared. Now that's obviously not what we started with, but that's our base graph, 1/x squared. Very nice, easy graph to start with. Now getting back to what we just mentioned, if the coefficient of x there, which is what I call b, if that's negative, then that 1/x squared graph would have been reflected about the y-axis. But that 8 is not negative, so we can go ahead and forget about that little piece of advice there, because it doesn't pertain to this problem, at least this specific function. Now we move on. What if the magnitude of b is greater than 1? Well, if the magnitude of b is greater than 1, then f is compressed, which is the opposite of what most people would think, but f gets compressed horizontally by a factor of 1/b. Technically, it's 1 over the absolute value of b, but whatever. So the larger that b is, the more compressed horizontally that our function gets. And it gets compressed by a factor of 1 over that b. Well, looking at our function here, that value of b is definitely greater than 1. So I know that this is going to be, this graph that is going to be compressed towards the y-axis by a factor of 1/8. Now, despite the fact that this is actually the winner, I'm still going to write out what would have happened if the magnitude of b was between 0 and 1, just for completeness. So if the magnitude of b is between 0 and 1, like a half or something like that, then f gets stretched, the opposite of what you would think. It'd be stretched by a factor of the reciprocal of b. So again, if that b, this coefficient of x here, let's just pretend for a second it was a third. That means that the graph would be stretched by a factor of 3, the reciprocal of 1/3. So inside the function, things kind of work opposite and reciprocal of what you're used to. Again, I get to cross this out because that's just not the case that we're dealing with in this specific problem, so I'm just getting rid of that statement. I then look back at my prototype function and I move through this alphabetically and I look at C now. C is what we call the horizontal shift, or it affects the horizontal shift. So here's kind of a weird thing, the way I write it. And I'm not sure I like the way that I write this, but it is just what it is. If C is positive, F gets shifted left C units. If c is negative, then f is shifted right, the absolute value of c units. The reason why I need that absolute value in there is most people will correctly actually write this as x minus c. And then they'll say, well, if c is positive, it moves so many units, right, and if it's negative, it moves so many units left, because the negativity is built into this piece. However, most students, and myself, I'll include myself in that group, just don't automatically write things with minus signs. So here's my advice to you so that it's easy to remember. What turns this statement into 0? Well, the opposite of c. That's where our curve gets shifted. Okay, let me give you an example of this. So if we go back over to our function we're going to graph here, notice if I asked you what would turn that parenthetical statement into 0, you would say a half. So therefore, this curve has been shifted 1/2 units in the positive direction. It's basically the opposite of this sign right there. It goes along with what I just said anyway. If c is negative, which it is, right? In this case, our c is a negative 1/2, then f gets shifted to the right. How many units? C units. 1/2 units. Technically absolute value c, but whatever. So the winner in this case is the second line, and we'll just go ahead and cross out the line that we didn't use. And I think of all of these lines, the one that everybody gets is this last one, the plus d. That's how far up or down the curve has been shifted. And there we have the rules. And let's just see what is the case for us right now. We have a +1 that's playing the role of d. So this curve gets shifted up 1 unit. So I'll just go ahead and highlight that here. And we don't need this guy. All right. So essentially what we said is we have some curve. It's based on 1/x². And what we're going to do is reflect that about the x-axis, squish it vertically a little bit, squish it horizontally a little bit, shift it to the right 1/2 unit, and shift it up 1 unit. Now, step by step, I'm going to go through this. But to be honest with you, when you do something like this, you don't have to be super accurate at the beginning, but your last graph has to be very clean. So let's start with just a really kind of a chicken scratched graph here. This is 1/x². 1/x² goes through 1, 1 and -1, 1. And those points are going to be critical for us to keep track of. Also, another thing that's going to be critical to keep track of are the vertical and horizontal asymptotes here. These will be like our guidelines to graphing. It creates kind of a target, and the center of that target is what moves when we move things left or right, or up or down. Applying the negative, we're just going to reflect that curve about the x-axis. Notice I'm not being super duper nice with and clean with my graph. I just want to get a graph going on here. Again, I would draw my vertical and horizontal asymptotes just to make sure that you are paying attention that they're there. Now I'm going to take care of the 3/7, and the 3/7 is going to squish things toward the x-axis. Everything gets compressed or squished. In other words, you're multiplying all the y values by 3/7. Again, I'm not really concerned right now about accuracy more than just that I keep track of points. So remember, this point was at 1, -1. Now it's at 1, -3/7. This point right here was at -1, -1. Now it's at -1, -3/7. And again, this is the new graph, y equals a -3/7 times 1/x². Each step of the way, I'm just gluing on another piece to our function. Reading from left to right, let's go ahead and take care of the 8 that's on the inside of our argument there. That 8 is going to compress things horizontally. All the x values will become 1/8 of what they were before. That's critical to remember. A lot of people don't remember that part. But the reality is, when you have a coefficient on x, it causes, other than 1 that is, it causes either a stretch horizontally or a compression horizontally. If that coefficient is greater than 1 magnitude, then it will cause a compression horizontally by a factor of 1 over that coefficient, in this case by 1/8, which just means I'm going to multiply all the x values by 1/8. So let's go ahead and do that. Look at these x values right here. They're going to become 1/8 of what they originally were. And just for completeness, I'll quickly sketch in my asymptotes, because now I'm going to use them. The next step, again, reading from left to right here, I've already read the negative, the coefficient, and the coefficient of x as well. Let's go ahead and take care of this -1/2. The -1/2 will shift our graph 1/2 units to the right. Notice what I'm doing here. I'm actually redrawing my asymptotes first. They shift 1/2 unit to the right. All of our x values you'll add a half to. So 1/8 plus a half is 5/8, and a -1/8 plus a half is 3/8. So that point right there is a 3/8, -3/7. Again, this is very dirty, quick graphing right now, but in the next step, I will have a very clean graph. The next step is the last graph, and all we're doing here is adding 1, which means we're lifting this entire graph up by 1 unit. And notice here's when I bring out the big guns. I bring out an actual ruler, mainly because I want to be accurate. So let me go ahead and measure everything out. So look how clean that is so far. I really did measure out like a half a unit and 1 unit, that type of thing. And now I'm going to go ahead and just add 1 to all the y values of the points here. And I'm going to plot the points first. So I'm not actually going to draw the curve first. I'm going to plot the points first. So those 2 points are now the adjusted or lifted points that were here. We just added 1 to the y values to make them 4/7. And from this point forward, you can actually just draw out or sketch out the rest of the curve. You know what it looks like. And that is the actual graph of g of x. Very nice graph. Notice how clean this is. Also notice that I expect my students to draw this cleanly as well. One thing that you should note here is we are being asked to graph that function, but then being asked to graph the absolute value of that function. And that's really where the pre-calculus comes in. Not very much of a huge step more than what we just done, but when you're asked to graph the absolute value of a function, first thing you're going to do is graph the function itself. Then you're going to note, well, what the absolute value does is it takes anything that's below the x-axis here and it forces it to be the positive version of itself. So essentially what it does is it reflects the curve above the x-axis. And this would be the graph of the absolute value of g of x. Note a couple things here. One, a function can never touch its vertical asymptote. So this function will never touch its vertical asymptote, nor will it run into it. The second thing you need to note, a function can cross its horizontal asymptote. No matter how many times I say that, people always ask that question. Wait, I thought that functions can't cross an asymptote. No, they can't cross a vertical asymptote. They totally can cross a horizontal asymptote. In fact, an infinite number of times if that's the way the function is built. So this, again, is the end and beautiful graph that we were looking for. Let's see what else we're doing in this video. So the graph of a function has been given to us, and we're asked to draw the graphs of these two following functions. I'm actually going to graph it right on that grid if I can. The first one is -1/2 f of x plus 1, and then the -1. Remember, the negative reflects the graph about the x-axis. The 1/2 compresses it vertically, basically multiplies all the values by the y values by 1/2. The +1 on the inside, you would ask yourself, what would turn that into 0? -1? Great. So this would shift the entire graph over to the left 1 unit, and this would shift the entire graph down. I'm going to do 2 moves at once. And apparently I didn't give myself the grid to do the graphing here, but let's just go ahead and do it anyway. I'll use green to graph this. It's going to be reflected about the x-axis. That's a chicken scratch graph real quickly, but I'm going to multiply all the y values by 1/2 as well. That's why I just only chicken scratch that out. So reflecting this about the y-axis, well, that y value becomes a -0, which is still 0. And this y value right here, which is at a y value of 3, becomes a -3/2. In other words, probably right about here, a little bit underneath the -1. So I know that the curve looks something like this initially. We'll be erasing it. Actually, I don't even need to erase it now that I think about it. And then what we're going to do is, let's see, this value right here was at x equals 3, y equals 4. So when x is 3 with the -1/2 version of it, it's going to be at 3, -2, which might be around here, honestly. Now, I don't want to fool you into thinking that that's the final graph. That is just -1/2 f. It's not -1/2 with any shifts. It's just -1/2 f. Now we're going to apply the shifts. And here's the beautiful thing about using a digital whiteboard. Remember, my shifts will move everything over to the left 1 unit and then down 1 unit. And there is my new graph. That's actually kind of a nice way of doing that if you have the capabilities of doing it. So, but it's a good way to visualize it anyway. So all I did was squish it, flip it, and then move it left 1 unit and move it down 1 unit. The second function, I'm going to take a moment to rewrite. It's -f of 2 times the quantity x plus 2. Now I can actually see the real horizontal shift. It's being shifted to the left 2 units, not 4 units, but 2 units. So before I do this, I'm going to go ahead and erase my previous graph. You could always rewind and take a look at that if you want. But I'll start with just taking the opposite of our current function. So I'll flip our function upside down, essentially. So you can see I took my time with that because I really wanted to get a decent graph of that. Hopefully I did. And now what we're going to do is apply the 2. So we've already applied the negative. Now we're going to apply the 2. Remember, the 2 compresses things horizontally by a factor of 1/2. So every x value you see in here will be 1/2 its original size. So for example, this green x value right here is going to start here now. It's getting squished to 1/2 the distance to the y-axis. And actually, that green dot, which was at x equals 3, is now going to be at x equals 3/2. Otherwise, everything else is pretty much the same. It can be argued that these x values on this curve right here are a little closer to the y-axis. They approach the y-axis faster, and that is true. And that's a short enough distance I can freehand a line right there. So what you're looking at in blue is -f of 2x. Now I'm going to take that graph and I'm going to shift it left 2 units because of this shift. So I'll take that graph and I'm going to move the anchor point that's on the x-axis over left 2 units. And there you go. That is the graph of -f of 2x plus 4. I'm not going to lie, it was actually nice to do this problem using a digital whiteboard because you can kind of wrap things up and move them left, right, or up or down. But you should be able to do that freehand on a piece of paper as well. Not obviously moving things like that digitally, but at least you can redraw on a piece of paper pretty decently. Now this is the greatest integer function that we did in a few videos ago in my series on graphs of functions, basically a prelude to calculus. And the greatest integer function is the step function. If you need to remind yourself of that, please go see that video. But I will have to assume that you've already seen it so that I can actually do this within a limited amount of time. So normally, the greatest integer function of x, just very quickly here, looks like the following. You have a solid dot, and it goes over, and at time 1, by the way, these are all units of 1 here. It's an open hole, and then it hops up this. It's a step function. But what we're going to do is we're going to multiply this function by 3, which means that all of the y values become 3 times what they originally were. So for example, this, which was sitting at a y value of 1, is now going to be moved to a y value of 3. And this guy right here, which was at a y value of 2, will be moved to a y value of 6, which I don't actually have graphed. but it's something like that. So now what you're looking at is 3 times the step function. Now we're going to take that function and lift it up just a half a unit. And it looks, well, sort of like that. I did lift it up half a unit, but because of the way that I drew my axes, it actually lifted the dots that I planted on my axes there. So I should probably erase those just to make them not visible. Same thing with these ones right here. There we go, something like that. So that is just the stretched and shifted greatest integer function. Now this has something to do with the next question, which is sketch a graph of the function 3 times the greatest integer of the absolute value of x. And this is slightly different than the absolute value of 3 times the greatest integer of x plus a 0.5. So in other words, this is not the same as the absolute value of 3 times the greatest integer of x plus a 0.5. They're not the same functions. If I was dealing with the absolute value, this case right here, that would actually be somewhat easy to deal with. I would just take anything that's below the x-axis and I'd reflect it to be above the x-axis. However, what an absolute value does on the inside of a function, so let me maybe write this in blue down here. So there's my 3 times the greatest integer function of the absolute value of x, then plus 5. That is very, very similar to the g of x function we see up here. The only difference is when x goes negative. So if x is positive, do I need the absolute values? If x is already positive? No. If x is already non-negative, is probably a better way of saying that. If x is non-negative, then the greatest integer of the absolute value of x is just the greatest integer of x. So as far as I'm concerned, when x is to the right of the y-axis, well, our picture will not change. However, when x is to the left of the y-axis, what ends up happening is that the function, let's say I plug in, what was this, like a negative 1/2. So if I plug in a negative 1/2 into the original step function, it would plant itself down there. However, plug a negative 1/2 into the step function of the absolute value, and the step function acts as if you plugged in a positive 1/2. So the function value will be equivalent to that had you just plugged in a regular positive 1/2. That is, the output should not be way down here, it should actually just be right here. And in fact, if I were to try to plug in negative 1, well, normally the greatest integer of negative 1 times 3 plus a half would be all the way down here. But if I plug in a negative 1 into the absolute value here, well, y, which is equal to 3 times the greatest integer of the absolute value of x plus 0.5, is going to react as if I just plugged in 1. And that will just be 3.5, or in other words, this point way up here. In essence, what's happening is you get a reflection about the y-axis of whatever's in the 2 rightmost quadrants. It just creates a reflection and you get to erase the stuff that was negative. But essentially what it's doing is it's taking whatever was over in these 2 quadrants and just rotating it over here. And that's kind of the good way to think about absolute values. In the original case, the one we did in the beginning of this video, it takes everything, the absolute value of an entire statement, takes everything that was down here and flips it up. Well, if you have f of the absolute value of an entire statement, it takes anything that was over here and flips it this way. Now, flip is kind of the wrong word here, but the reality is, in our first case, the absolute value of the ugliness, anytime your function dipped below the x-axis, you, instead of dipping into the lower quadrants there, reflected and had it go that way. In f of absolute value case, you pretty much ignore any of your graph that you would have done over in these quadrants right here. You completely ignore those and you just do a carbon copy of whatever you had in these quadrants. So for an example, if when x is positive, your graph looks like this, maybe on the other side it looks weird. Let's pretend that f of x on the other side looks like this. What f of the absolute value of x does is it says, okay, well, when you're graphing the positive x values, well, it's the same function as if, because positive x is the same thing as the absolute value of x. So to the right of the y-axis, everything's the same. But to the left of the y-axis, the function never thinks you're plugging in a negative number. So it ignores all that and it just duplicates this graph. It's a really cool way of thinking about absolute values of functions versus functions of absolute values. Absolute values of functions flip things to the top two quadrants, quadrant 1 and quadrant 2. Basically flips things above the x-axis. Functions of absolute values of x, on the other hand, mirror the values of the function from the positive x values over to the negative x values. Now, I want to be very clear because I don't think I have been up to this point. When I say functions of an absolute value, I mean functions of the absolute value of x, not functions of the absolute value of, say, x squared or x minus 2 or x cubed plus x plus 1 or anything like that. So everything I've mentioned about functions of absolute values is only true if it's actually functions of absolute values of x and x only. The absolute values can't be on anything else. So those skills are semi-important in calculus, so it's probably pretty good that you watch this video. And I hope that I haven't bored you too much, and I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't whine. Just